Ja, vielen Dank. Oh, I will talk in English. Many thanks for inviting me to talk about my studies on epidemiological research of childhood cancer, especially leukemia, near nuclear power plants in Germany and other countries. I will start. Let me see. I hope that will work. Okay. In Germany, we started to have the first epidemiological study on cancers near nuclear power plants in 1992, commissioned by our German government or environmental ministry, and conducted by our cancer registry. It was published in 1997, and it was a traditional ecological study, which means that counties around nuclear power plants were used on county averages of, let's say, nuclear cancer rates, and distances were used. So it was not individual data, so we didn't look at individual distance of a child from the nuclear power plant, but it was averages on district averages. Well, that is cheaper and quicker to do. So this study used two endpoints, all cancers, all malignancies, and acute leukemia. Study regions were 15-kilometer zones with all communities that fall within these 15-kilometer zone. Around 20 sites of nuclear facilities. Among them were 15 nuclear power plants and 5 other nuclear facilities. The control regions, to compare the incidence, cancer incidence in the regions around nuclear sites, we needed to compare with other regions away from nuclear sites, like 30 kilometers and more distant from these nuclear sites. There were also 15-kilometer radius or 30 kilometers diameter. The standard incidence, the rates in the incidence rates, let's say, in these areas around nuclear power plants were compared to the cancer incidence rates in of the control regions. So that's called, the ratio is called the standard incidence ratio. And these standard incidence ratios were then calculated in different distance zones, 5-kilometer distance, 5 to 10, and 10 to 15-kilometer zones. Comparison, the analysis of the pooled data sites was presented for 1980 to 1995. Oh, we had a 16-year study period then available. Because the cancer, our cancer registry for childhood cancers only started in 1980, so the study could only start in 1980. There were black dots on this map. The map represents Western Germany. That was before the unification. So black dots are the regions around, the 15-kilometer regions around nuclear power plants. And the gray zones, the control zones, so these areas that served as control. This is one of these study areas around, or study regions around nuclear power plants, and you see the different communities in this study region, and the colors say to which, whether they were, they belong to the 5 kilometer zone, the 5 to 10, or the 10 to 15 kilometer zone. And yeah, what I said before, the relative risk was defined as the standard incidence ratio in the study area to the standard incidence ratio in the control area. And standard is always the observed cancer cases divided to expected cancer cases. The expected are calculated taking the age distribution into account. When cancer is dependent on age, so you have to take the age specific cancer rate into account and the population distribution. With you have younger people, more younger people, or so. But this study was used for children under 15, but also with a focus on children below 5. Yeah, and then the p-value was calculated, meaning the probability that the result of this comparison is statistically significant or not. P-value is just the probability. If it's greater than 5%, then it's not a significant finding, and you call it a chance result, or you assume a chance result. So significant means that the p-value is smaller than 5% or 0.05. What was the result of the KIC study? We found no increased risk overall. The relative risk in the study area was 0.99, so just like what we would expect. So, but in the near zone, in the 5 kilometer zone, there was a slightly increased risk, which, however, was not significant, far from being significant. 0.04 for all children below age 15. The risk was slightly higher for children below age 5, but also far from being significant, only 10% increase. But there was an increased risk of acute leukemia in children under 5 at the lowest, the nearest distance zone, in the 5 kilometer zone, which the relative risk was just 49% increased. So 1.49, the relative risk. And this was at the it was not quite significant, it was 0.06, and so a little bit above the significance limit. But that was an indicator that there might be an increased risk. In this study, however, a two-sided test was used. In the following study, in the KIC study, a one-sided test was used, which means in the first study, in this study here, they looked whether the incidence, the measured cancer rate, was equal to the cancer rate that was expected. So whether the relative risk was 0 or compatible with 0 or not. This is called it could be smaller or bigger, the risk, when you test in this way with a two-sided test. But if you take a one-sided test, you look for an increase. You say, okay, we are not interested whether the risk is smaller than expected. We are only interested whether it's higher than expected. And in this case, you would use a one-sided test, which is sharper because the p-value is just half of the p-value for a two-sided test. So if you would have applied a one-sided test, this result would have yielded a p-value of 0.03, which is significant. So it's marginally significant, this result. And in the KIC study, for good reasons, the next study that followed, for good reason, the one-sided test was applied. I did a reanalysis of this data in 1998. That was the year when I started to work at the Environmental Institute in Munich. And they asked me to just check the data of this. So I got the original report from the IMSD that conducted the study, and I looked at the study, and I found out that they didn't include only nuclear power plants, but there were 5 sites of nuclear facilities that had nothing to do with nuclear power plants. There were research reactors, neutron sources. I'm also a neutron physicist, so I used neutrons for doing my PhD. The research that only produce neutrons for physics research, and no electricity. And then there were others. One, for instance, a nuclear power plant that never went to in operation because it was built on a geological zone, you know, and it was a dangerous place, so they didn't get permission to operate. Or it was built and didn't operate. But it was ready. It's a museum nowadays. So they included that also. And then there was another site of a test reactor which was very, very small, only 16 megawatt electrical power. Nowadays we have 1,300 megawatts, nearly 100 times bigger. Well, they included that, and this was shut down in 1985 already. So, and then another one, a test reactor first, a prototype reactor, a high temperature reactor, which has worked only for about 400 days, and then it was shut down because everything broke down. This was just called just a catastrophic reactor because it never really worked. So all these sites were included in the study. And I just excluded these sites and just concentrated on commercial nuclear power plants, the normal nuclear power plants that we use nowadays. Focus on the 5-kilometer zone, because in the first study we found an increased risk, if ever, we found it in the 5-kilometer zone. And I looked at children below age 5, because also in this age segment we had an increase. I used the one-sided test instead of the two-sided test. So, and with this study, I published that study a year later in an American journal. We found quite different results. So, for all cancers, in children below age 5, I found a 54% increased risk, which was significant. As you see with the p-value, it's in red up there, it's 0.0034, so it's clearly significant. And in boiling waters reactors, it was 0.0077, and the boiling, it was 70% increased. In pressure water reactors, 40% increase. Let's see. Here's a plot of the standard relative risk in these different categories: boiling water reactor, pressure water reactor, all nuclear power plant sites, and the other sites, not nuclear power plant sites. And you see that because the other sites had a reduced risk, only 0.48, so the risk was half of the expected risk in the other sites. The other one was 50% increased, so that matches more or less. So the risk, overall risk for children below age 5 was 10% increased, and not significant, but if you look at only nuclear power plants, we had a 54% increased risk. The risk for leukemia in children was higher, was 0.74, so 76 or 76, so 76% increase. Now, after that study, there was a real uproar in the media, and was published, and it was in the television and so on. So there was much rumor, and the German Radiation Protection Agency, they had to react. And so we had a government change in this year, in 98. By the end of 1998, we had a red-green coalition, and the Green Environmental Ministry, they ordered then that a new study was done. And because of my study, so they ordered the KIC study. I had to present my results there, and we have how do you call it? Bundesamt für Strahlenschutz, Federal Office of Radiation Protection, it's called in English translation. So, and they asked me to come and present my results, and they were convinced that it's necessary to redo the study with, however, a better study design. They say we now want to apply a state-of-the-art study design using a case control study, which means that you look for the location of every child and every control child. So a very precise distance definition, because the location is defined by the house, and the house is a small place, so they could define the distance very precisely. So this study was started in 2003, finally, and was then published in 2007. And they established, the first time ever, they established an external advisory board that also included some people that were against nuclear power, like me and other people. We were in a whole, we were 3 people that were anti-nuclear in this external advisory board, which was novel, which was never before had happened. So this was, as I said before, a case control study. So a case is a child with cancer, a control child is a child without cancer. And so you look for all in a defined site, in a defined surrounding of the nuclear power plants. You look for children with cancer, and to each child with a cancer, you select 3 controls in this case. That's called a matching of same age, same sex, and within this reactor site area, or surrounding of this reactor site. We looked at all malignancies, or they looked at all malignancies and all leukemias. They included all German nuclear power plants, split up the site because one side of these 15 sites had a new reactor, so it was 2 kilometers apart, so we had altogether 16 sites. They looked at children under 5 because, as I said, this was the target group, was the group that already before had shown increased risks. As I said before, we had the possibility to define the distance very well, and now data were extended to a study period of 1980 to 2003, and the one-sided statistical test was used. This was then the study zones, and the count is in vicinity to the NPT sites. So all colored areas were the study areas. So this will cases, control numbers, and so on. The risk increased. That was the main result, with decreasing distance from the nuclear power plants, and they found that the trend of the risk with distance was very significant. The p-value was 0.0034 for all cancers and 0.0044 for leukemia. Then you can evaluate the data comparing the ratio of cases and controls in the 5 kilometer zone to the ratio of cases and controls in the region 5 kilometers and further. or farther. And you find a 60% increase for cancers in the 5 kilometer zone compared to larger distances. And you find a 110% increased risk for leukemias. To date, the TIC study is the most powerful study worldwide in this area. Nobody else has done a case control study, children around nuclear power plants. So, all malignancies, that is what we found. You see, now with this model, we call that a model, the line, the blue line, this is just an expression, mathematical expression of the distance dependency. In this way, in this diagram, distance dependency is 1 over r, that is 1 over distance. So with this model, you find it significant. That was the result that I presented below. What was not considered was another model like this one. This is a 1 over r squared, so 1 over the square distance. This fits the data better than the other model. And the best fit is for leukemia. This is what we found with a 1 over r model, 1 over distance model. So you always find a very high increase in the smallest, the nearest distance zone, and then you don't find any effect. At far distances, you don't find effects. This is what you find with a combined model with a 1 over r distance and 1 over r squared distance zone, which linear quadratic model, it's called, the regression model. So you find that that fits data better than all other models. And then this model here is just a comparison of the rates in the 5 kilometer zone to the rates in distances above 5 kilometers. So in fact, you see no increased risk beyond 5 kilometers, at least not in the German data. And for leukemia, and also for cancers, we find increased risk at farther distances. So now, what they say in when they presented the study and what they write in their technical report is, for instance, they say that near one of these nuclear power plants, they measured they estimated the dose. And they say the dose is, and then they make 0.0000019 millisievert per year, is something like 1 millionth or 1 microsievert per year. No, 1 nanosievert per year, excuse me, because it's, so it's absolutely minimum. Now, when you look at the government reports, the German government reports, which are annually published, they say for exactly the same Obrickheim, you find the number of 0.0032 in a 10 years average. If you compare these values, it's more than a factor of 1,000 different. So, and then also they say the leukemia risk. Then they give a risk for a 50-year-old male. The doubling dose for cancer being 2,000 millisievert. But we have to do with 5-year-old children. And they don't talk about that. And we know that cancers that are induced in childhood, or especially for the first 5 years, are usually induced already in utero. They are in the embryos. So in this sensitive phase of embryogenesis, that's when you expect that cancer or leukemias that appear in the first 5 years are induced in the first trimester of pregnancy. And for this group, target group, the doubling dose is considered some millisievert, not some thousandth millisievert. So another factor of 1,000 difference. So this is how, yeah. And then what they say also is, I mean, if you want, so it can be translated in German, but I say, based on present radiological or radiobiological knowledge, ionizing radiation from NPPs cannot be interpreted as the cause for increased cancer or leukemia rates near nuclear power plants. And they say, with this study, it's not possible to decide whether confounders, selection bias, or pure chance may have played a role. So they say, okay, we find an increased risk, there's no doubt about that, but it cannot possibly be explained by radiation. There must be some other reason. But now, what are the concerns we have with this official dose and risk calculations? Because risks are not measured, or also the doses cannot be measured. They can only be calculated by assuming many things, like what comes out of the stack, the isotopes, then how they are transported or so, the propagation, they have propagation models, they are simplifying the real propagation, they are idealized, sort of, and they have errors, of course, estimating errors. They cannot be precise, but it can be a factor of 10 higher or lower, more or less. Then there's some doubts about how they consider the biological effectiveness of tritium, for instance. Then the dose factors, especially for short-range beta emitters like, for instance, tritium, and so are in doubt. They are probably too low, much too low. And then the increased radiosensitivity of the embryo is not taken into account normally when they consider risk. What happened after the KIC study? First, the results were externally verified by Professor Darby from Oxford University. That was one of we as an advisory board, we asked them to verify the data. They sent all the data to this Professor Darby, who then re-evaluated the data and confirmed the results. So they said, so everything is fine. And then we have a Nuclear Safety Commission, Strahlenschutzkommission in German. They were asked to give an assessment of the study, so evaluation sort of the study. An additional evaluation was then done a year after. That was now done with an ecological study design. That was more or less to compare the two methods, whether with the same data, if you change the study type in this way from a case control study design to an ecological study design, that would give the same results. It was not the case. For leukemias, they only did it for leukemias. They found only a 44% increase instead of a 110% increase, which the study, the case control study gave a 110% increase. In the 5 kilometer zone, this study design, the ecological study design, based on the same data, gave a 44% increased risk. So you see, the study design plays a big role. And we said this case control study design is superior to this ecological, where you average everything. Then from 2010 on, several other studies were published in other countries in Europe. The first one was in Finland, but in Finland, in the 5 kilometer zone, all nuclear power plants are on islands, so nobody lives in only some employers. So this gave no case, so you couldn't do a study there in the 5 kilometers. They extended them to 15 kilometers, but case numbers were so small there was no chance of finding anything. But they did another study in Switzerland, and one in Great Britain, and one in France. That was only published 2 years ago in France, but the other 2 were published in 2010 and 2011. All with a more or less ecological study design on a county basis or on a district basis, and so all these studies found increased risks in the 5 kilometer zone. All these studies didn't find an increased risk in the further distant zones. So the results were very comparable to the German data. But because of the small numbers, all individual studies were not significant. All results were not significant. I listed here the results for Switzerland, Germany, France, Switzerland, Great Britain, France, and Germany. And you find, when you look at the last but one column, you find the relative risks. Just comparing the 5 kilometer zone to the 5 to 15 or 5 to 25 and 5 to 20 or 5 to 30 kilometer zone. And you find that the risk in Switzerland was, for instance, 46% increased and 39% increased in Great Britain, 48% increased in France, and 45% increased in Germany. And altogether, as an average, you find a 44% increase, and which is, as you see here, 0.0017 is highly significant, or nearly highly significant. So pooling the data gives you highly significant results. And this, as for the moment, we don't have other studies worldwide. That is the only study there are, because this is only done after the tick study and there's not much time left. The Americans are now doing a study. There's no results yet, and whether they do it the same way, and so whether they are comparable, the methods are comparable, we don't know yet. So, but for the moment, that's the only existing studies, and they all give increased risks, and the combined data, the pooled data, give a highly significant result. So this is the data points for in different distant zones for the different studies, and you see, you find these increased risks only in the 5 kilometer zone. In the 5 to 10 kilometer zones, 3 out of 4 studies give a reduced risk, not significantly, but reduced risk. And the best fit to the data is by a regression using a linear quadratic regression model. So a linear term and a quadratic term. That is the green line. The other, the interrupted or the broken line gives you 1 over r distance dependency, which is less, which fits the data less well than the other one. Then combining all data sets, this is the individual data, and this is when you pool the data, you find this behavior. So that confirms very well this approach, this linear quadratic dependency. I published this together with Ian Farley from Great Britain last year. We published that. It was accepted by the International Journal of Cancer, pretty highly renowned paper. So we have a problem. We find clearly increased risks near nuclear power plants, but the exposure is considered to be some millisieverts, some microsieverts, excuse me, the dose. That's the calculated dose, but nevertheless, the best estimate is at some microsieverts per year. And we know from studies of medical studies that the probably a doubling dose of leukemias is after in utero exposure is some millisievert. So there's a gap between our observation and what we expect. We expect a 1,000 times smaller effect than we really see. So, but now we can say we are not very sure whether these calculations are reliable. The models used for the propagation of the nuclear cloud emissions might have a factor of 10 error, you know. Then the internal radiation, they say our calculations of internal radiation, that is radionuclides that are incorporated by the air and by the food, are probably in error, also by about a margin of 10 or so, a factor of 10 plus minus. And you know, all these uncertainties accumulate, and have here and there, so the uncertainty widens. But still, even if we accept something like a factor of 10 to 100 uncertainty, it still is within the legal limits, because our legal limits are very much higher. We're not in the microsievert level, but we have 300 microsievert so they would still be within the legal limits, these emissions, even considering all these uncertainties. So even though we consider these uncertainties, we are still off by a factor of 10 to 100 from a rational explanation. So the question is how to close this gap of knowledge or of explanation. We need to explain a factor of 10 to 100 to explain our results. So what we usually do when we calculate doses, we average over 1 year. We say the dose over 1 year. And we don't consider the moment of dose, whether we have peaks in the emissions or so. We just consider an average dose, which is okay if we consider that there is a linear dependency of dose and risk. But only then you can average. If there's not a linear dependency of dose with risk, or of risk with dose, risk increases disproportionately with dose, then this doesn't work. You cannot average. That's one problem. So that is called the dose response curve. How is the risk increasing with dose? Is it a linear curve or is it an increasing curve, for instance? And then we don't consider the variations, as I said, whether there are spikes that where when you open the lid of a reactor, a lot of radiation comes out instantaneously. Within some hours, you have a high peak in radiation emission. All these spikes are averaged out, because they only give the average dose. So I go to here. I found this slide called Strahlenbiologie, teratogenes Risiko in German, so the teratogenic risk. And they mentioned the uppermost line here, they mentioned cancer and leukemia as under this term teratogenic risk. So they consider cancer and leukemia induction in uteri is a teratogenic effect. Among others, like needless to say. So you see that is for mice. This is a diagram for mice, and you see when, in which period, organogenesis, for instance, these effects can take place, like induction of leukemia, and that are within the organogenic phase. And if you look now at another diagram that I found in the internet, they discuss in this what is a stochastic effect and what is a teratogenic effect. And a teratogenic effect, they say, is characterized by a threshold dose, by a dose below a safe dose, yeah? Below which no effect is expected. While a stochastic effect has no such threshold. So you have a linear dose response, so it's just a chance result. But a teratogenic effect is characterized by repair processes. And these repair processes, they say, lead to a nonlinear, a curvilinear dose response. This is not considered in all these considerations or in all these calculations of doses or so. It's not considered in the risks. So when you do some statistical considerations how this can be explained, you just accept that doses and especially radiosensitivity in small children are characterized by distributions. They are not all equal. Not each child has the same radiosensitivity, but there is sort of a distribution curve. Normally you assume a log normal distribution for the sensitivities and the doses. And if you take these two curves into account and just consider both the distribution of doses and the distribution of radiosensitivity, you arrive at also, as the effect of the two influences, you expect a accumulated dose response, accumulate log normal distribution for the dose response. This is the most likely dose effect or dose response model that you can have when you accept the teratogenic effect and when you accept that doses and risks are sensitivities are characterized by normal distributions. So that's what you expect to find then as a dose response. Here the x-axis I set annual dose and multiples of background dose. If you show the number 1, the value of 1 is background dose. Now double the dose in the background dose and you will see the risk that you would expect from this curve for a double. If you have, instead of 1 millisievert per year, 2 millisievert per year. And you see it's much, much more than the double risk. Because at 1 unit of background dose, you practically don't see any effect, while at 2, you have a considerable effect. Yeah? Perhaps 20 or 50 times more. This all depends on whether the doses are now equally distributed over the year or not. And this is obviously not the case. If you look for time for refueling in one of these reactors in Germany, the Gundremmingen, the biggest nuclear power plant in Germany with 2 boiling water reactors, 2,600 megawatt, more or less. And you look at what radiation emission from this, you see here, before the refueling period, in the 19th of September, you don't see any deviation from the null, yeah, from the zero line. But then, when they started to open the lid, within hours, the emissions spiked to the maximum is 500 times higher than the normal rate, the normal emission rate. That's noble gases, what you see here. And goes down within days, you see. But when you now change the scale from a linear scale in the vertical axis to logarithmic scale, you see what the normal rate was a week before this. That's the gray dots. The gray dots is the normal emission rate before refueling, before they opened the lid. And then you see that there's a difference of about a factor of 500 to the peak value. So it's shortly a very high rate. This is just a way to, it's not so important, for different nuclear power plants, what they calculated as the dose, annual average dose. Gundramingen is here at 0.006. It's 6 microsieverts for Gundramingen, the value they give. But that is, as I say, with all these possible error sources. So, I don't know, it might be 60, who knows. Here I show a plot where you see the dispersion or the propagation of the nuclear cloud from a nuclear reactor. If you look at 0, that is the farthest left point, and in the direction of the wind, and that's vertical to the direction of the wind. So you see, then you see where the isolines characterize the radiation level and you see that it's many orders of magnitude. You see that on the left side. In all these lines are a factor of 10,000 between the lowest and the highest isoline. And you see the highest risk you find in some 2 to 3 kilometers distance from the reactor. You don't find that immediately near the reactor. The highest risk you find 2 to 3 kilometers from the reactor, because the cloud comes down to the ground only at certain distances. Our nuclear power plants have a stack that is 160 meters high, so it takes a while to come down. Of course, these calculations are idealized. No mountains, so it's just a flat plane and so on, calculated, and a steady wind speed and so on. So, but nevertheless, it gives you an idea that our assumption of a 1/r distance dependency cannot work, because certainly it doesn't go to infinity at 0 distance. So that's an approximation for farther distances, but it's certainly not true for the nearest surrounding. So we expect in the 3 to 5 or 2 to 3 kilometer zone, we expect the highest risk. And now, if we look at in this report of the KIC study, there was a diagram showing all cases and controls that were found in distant zones. Of course, they had a large region of 50 kilometers that they showed in their panel. I haven't shown that yet, but I used only the 5 kilometer distance now, and then I counted all points for the, because I asked them to give me the cases in the 3 kilometer zone to verify that the risk in the is not higher near to the reactor than a little bit farther away. They refused to give me any data. So I counted data points and found that there were 21 cases and 50 controls. And with this number, you can do the same thing in the 3 to 5 kilometer zone, and then compare the ratio of cases and controls in the 3 kilometer zone to the cases to controls in the 3 to 5 kilometer zone. And I found out that the risk, in fact, in the 3 kilometer zone is smaller than the risk in the 3 to 5 kilometer zone. That is, the red curve shows the cancer risk. And you see, I find that the right scale here, the right vertical scale shows you the relative risk. And you see that near the reactors, in the 3 kilometer zone, you find a 30% increased risk. But in the 3 to 5 kilometer zone, you find a 70% increased risk. And from that on, in the 5 to 10 and so on, you find no increased risk. Up there, the green line shows you the sex ratio, that is the ratio between male and female birth. And this, strangely enough, you find the same distribution for sex ratio than for for cases of cancer in this case. Also a peak in the 5-kilometer zone. So I tried now to put together all information, the noble gas concentration that I found while refueling. Then I took my dose-response relationship and took the emissions, and altogether I used for calculating the risk under the assumption that the official dose that is given as an annual average is a factor of 10 too small. Because I said let's assume that it's not 6 microsievert, but 60 microsievert, something like that. With this assumption, in this case, I calculated 50 microsievert instead of the normally given some microsieverts. So with 50 microsievert, taking into account the curvilinear shape of the dose-response relationship, yields a risk of 2.18, so a more than 100% increased risk just on the basis of the assumption that all that holds, that there's you only have to correct the official risk dose estimates by a factor of 10, then you can explain with these assumptions the risk we observed near nuclear power plants. So that would be, so that is the last one now. The leukemia in children is more than doubled. Official dose from nuclear power plants is some microsievert per year. Doubling dose for leukemia is some 1,000 times greater. Dose estimates are unreliable. That's what all say. Even they admit that those estimates have an error margin. The aerial radioactive discharges are highly episodic, mainly during refueling and inspection. And if dose response is curvilinear, effect increases disproportionately with dose. Conclusion, the result challenges the assertion of official radiation protection agencies that the radioactive releases must be ruled out as a possible cause of increased leukemias near NPPs. Yeah, thank you for your attention. Oh, I have one more just as to, that is all my material that you can find in the internet, and some of my websites also. Most of that is German, like the publication of the Strahlentelex in German, but some are in English. So thank you for your attention. Okay.